All right, welcome to part 2 of lecture 6 from Math 13. I know I said I would do 2 parts. I've decided to do 3 parts, so I'm just going to do this one, proving a universal statement by pushing definitions, as one video, and then in the last video I will do the last 2 topics. All right, what do we mean by pushing definitions? Usually when we say we're proving something by pushing definitions, it means we're just kind of leaning heavily on the definition and just kind of like unpackaging what does the definition mean and like sort of interpreting it from there, and then often the proof will follow relatively naturally once we've sort of unpacked what the definition is actually saying. So we're given this definition. We're saying an integer n is said to have remainder r 0, 1, or 2. So r can be one of those three. Upon division by 3, if there exists some integer k such that we can write n as 3k plus r. This might look a little familiar. This might look a lot like modulo, and that's because it is kind of related to modulo. So we're saying that like there's sort of 3 cases that can happen. Like n can be, 3k plus 0. So in this case, we could say that n is 0 mod 3. If you go back and look at the definition of mod, and I recommend you do, go ahead and pull it up and double check that you believe me that this is what we would get. And similarly, if you did n equals 3k plus 1, then we could say n is equivalent to 1 mod 3. And lastly, if you did n is equal to 3k plus 2, well then what would we get? We would get that n is equivalent to 2 mod 3. Okay, again, I really do recommend pull up the definition of mod and like test yourself. Do you believe what I just said? Okay, so we're going to work with this definition, and now we want to prove this theorem. We say if n is an integer, then n squared has remainder either 0 or 1 upon dividing by 3. Okay, so we want to show that like n squared, so let's do some brainstorming. We want to show that n squared is 0 or 1. So we want to show that it's like 3k plus 0, which just goes away, or maybe n squared is equal to 3k plus 1. Notably that it is not 3k plus 2. This is a strange result because, I mean, what's special about 0 and 1? Why can't it be 2? Also, the hypothesis is really weak. All we know is that n is an integer. So it's like we don't have anything to go off of, right? It's like, so this is a little strange. We don't want to use something like contrapositive because then we would want to be concluding that n is not an integer. And concluding something's not an integer is fiendishly difficult. So maybe we should just try to go ahead and like work with this definition that we've got, right? Let's just literally push definitions. This definition says that any integer like has remainder 0, 1, or 2 upon division by 3. So maybe we should, since we're going to be looking at remainders, maybe we look at cases where n is 3k. So when you get a remainder of 0, so it's multiple k, and then like n squared, what would that be? Well, it's 3k squared, and then we would get we distribute it 9 times k squared. Okay. Oh, but there's a 3 inside that 9, so maybe I can write this as 3 times 3k squared. Oh, look, that right there is an integer. And so, come on. What have we just shown? We've shown that n squared, like n squared is, or you could say, has remainder 0 upon division by 3. Okay, this is promising. And so like if we did this with like, if the n was 3k plus 1, then we do n squared. What would that look like? Well, we get 3k plus 1 squared. And we do some work. I think we're going to get something kind of similar. Okay, I'm kind of jumping ahead here. So if we're kind of like filling out this outline, I've kind of done some of this already. So if n has remainder 0 upon division by 3, it'd be n is equal to 3k plus 0, which is just 3k. for some integer k. If it has remainder 1, as we were saying above, it's 3k plus 1 for, some integer k. And if it has remainder 2 upon division by 3, you get 3k plus 2. Now we want to go ahead and make sure that each of these cases work. So for the sketch of case 1, well, I kind of did it above. So you get n equals 3k. And then what happens when you do n squared? Well, you get 3k squared equals, and then we did this above. We end up getting 3 times 3k squared. So notably, it has remainder 0 upon division by 3, according to this definition. Let's check the other ones. Let's make sure that they actually work out. So if n is equal to 3k plus 1, well, what does n squared look like then? Well, get 3k plus 1 squared. We're going to have to FOIL this out. So I think we get 9k squared plus 6k plus 1. Okay, we want to write this as like 3 times an integer plus either 0, 1, or 2. Okay. Well, let's look at what are the things that have a 3 in them that we can pull out front, right? So I think I see a 3 here in the 9, and I see a 3 in the 6, because 6 is 2 times 3. I don't see a 3 in the 1 here, so I'm going to leave it alone. So let's go ahead and pull a 3 out, so we get 3k squared plus 2k, and then plus 1 on the outside. Notably, this thing is an integer, and this would tell us, so the n squared has remainder 1, upon division by 3. Okay, that's looking good because, we want to show that n squared always has 0 or 1. So far, we've gotten a 0 from this case up here. We've gotten a 1 from this case here. So let's just make sure that case 3 gives us either 0 or 1 as well, and we'll be good to go. So what's the third case? The third case is when n is equal to 3k plus 2. And then n squared is going to be 3k plus 2 squared. Oops. We want to FOIL this out. I think we get 9k squared plus, oh gosh, do some math, 12k plus 4. All right. And things are a little tricky here because I see a 3 here and I see a 3 here, but then we got a plus 4 on the outside. Now we don't want to just pull out a 3 and then have a plus 4 on the outside because we really want it to be either 0, 1, or 2, right? That's the definition tells us it should be 0, 1, or 2. And I mean, like, if you remember back to division, right? Division also says the remainder should be, less than your divisor. So I'm going to do a little sneaky trick here. I see 4, I can write that as 3 plus 1. And then I got a 3, right? So I'm going to do that. So I get 3 and then plus 1. Oh, this is looking good because now I've got a 3 in each of these 3 terms. So I'll pull a 3 out from them. So we get 3, and we get 3k squared plus, what's this, 4k plus 1 plus 1. Oh, look, and now this thing in parentheses is an integer. So this says that, n squared has, remainder 1 upon division by 3. Okay, this is good. So it looks like in all 3 of these cases we get 0 or 1. So let's go ahead and write up the formal proof. Let's put all this together. So just for clarity for the reader, let's write what we can assume. So we assume that n is an integer. We have 3 cases, right? Now you could do it stylistically like I did in the previous video. We write case 1, colon, and then something case 2, and then case 3. In each of these cases, there's many of them. They're relatively small. So I'm just going to go ahead and write it like this. So if n has remainder 0, by division or under division, what was the wording? It had a remainder upon division by 3. Okay, let's make sure we match the wording. Upon division by 3. Then n is equal to 3k for some integer k. Thus, what did our scratchwork say? Well, we had n squared equals, and then we want to write out our arithmetic to convince our reader. We get 9k squared. Then we write this as 3 times 3k squared, where 3k squared is an integer. Just do it like this. And you could say, hence, n squared has remainder 0. I'm going to drop the upon division by 3 because it's clear from context that I mean upon division by 3 because I've already stated it above. If you're ever worried, you can always just, make it clearer and just write upon division by 3 every time. That's also okay. All right, we did one case. Let's do the next one. If n has remainder 1, then n is equal to 3k plus 1 for some integer k. Hence, n squared is going to be 3k plus 1 squared, which when we wrote out our arithmetic, we got 9k squared plus 6k plus 1. And then we needed to pull the 3 out. So we get this stuff right there. And then you could say since the thing in parentheses, 3k squared plus 2k, is an integer, n squared has remainder, what did we get? It has plus 1 on the outside, so it has remainder 1. Okay, we got one more case to do. So we'd say if n has remainder 2, then n is going to be what equation? 3k plus 2 for some integer k. Thus, n squared, substituting it in, we get 3k plus 2 squared, which when we did all our arithmetic, all these numbers, 12k plus 4, we wanted to split up that 4 to pull out that 3, so we get 9k squared plus 12k plus 3 plus 1. Pull out the 3, 3k squared plus 4k plus 1, and then plus 1 on the outside, a little hidden there. All right. And then you could say, since the thing in parentheses, 3k squared plus 4k plus 1 is an integer, n squared has remainder 1. Now, just to tie it all back together, just for clarity to the reader, we could say in each case, n squared has remainder 0 as in the first case, or 1 as in the other two cases. So the result holds. Okay, now Alessandro's proof does something very, very similar, but instead of saying, has remainder 0 as each of the cases, Alessandro writes n is congruent to 0 mod 3 or n is congruent to 1 mod 3. That is also perfectly legitimate because, as I mentioned up above, these ideas are equivalent. So you could use either language to prove this result. Either would be fine. Question: can we use without loss of generality? Did we have to do all three cases here? The answer, unfortunately, is yes. Because if we look at each of the cases, in each of the cases, these equations that I've got here, all these equations, this stuff right here, all that, they're all different. There's a whole bunch of ones, there's different numbers floating about. So we really do want to make sure that all the details work out in each case as we want it to. So we cannot use without loss of generality in this proof.